Well, hey there, guys. We have a low-tech video here talking about our popper lab. Thought I would give you a little bit of insight in case this is still eluding you and you are one of the groups that is still finishing up, coming in, or maybe you did the whole thing and you're thinking to yourself, why did I do that lab? That makes no sense to me. So I'm going to ask you to follow along in terms of the conceptual stuff of what we were doing and what we were trying to do. Now, of course, as you remember, we were using these lovely little poppers, all right, and they were such that you had to drop them in order to get them to bounce. And the idea was that you would drop them and they would bounce higher than they went before. So let's start with a picture of that, shall we? So here's your popper, and you drop it, and it hit the ground, and then it popped back up, and it went much higher than it did before. And something happened here. Of course, we realized there was a snap, right? The popper snaps, and that is the reason that the popper goes higher than it went in the first place, right? I mean, that's pretty obvious. So let's think about this in terms of snapshots and energy and what's going on here. And this is where a lot of the critical thinking piece takes place and can lead you in the right direction versus just trying to stare at a bunch of formulas and trying to come up with what am I missing. I think that's a mistake sometimes in physics, is to go straight to the formulas and try to just use formulas. All right, when you drop something here, right, if we draw an LOL diagram, actually let's draw a few LOLs. Well, what do we have in our system? Of course, we've got the popper, we've got the earth, right? And those are the two biggies. So at the very top here, what's going on? Well, I have height. So I've got potential energy, kinetic energy, spring energy. Well, I don't have any kinetic energy because I'm going to be dropping it from rest. Spring energy, you could probably argue that there is some spring energy here, but I'm going to say for now, let's say no. Okay? Because quite frankly, my next snapshot is going to be right here, right before it hits the ground. And even though the popper is inverted, you could say it has spring energy. It has the same spring energy, so that's boring. It's exactly the same. There's no change. So what has changed? Well, let's go back to our KE, US, and thermal energy, right, for our second one. Well, we're not dropping it from very high, so we're going to say no air resistance. We are taking all of that potential energy, and right as it's getting ready to hit the ground, it doesn't have any more height, but it is moving. And again, like I said, we could argue on the spring energy, but even if you drew a box or two here, you'd have exactly the same boxes over here because it's not changing. So let's just pretend let's just ignore it for now. Right, all of that potential energy is changing to kinetic. All right, so I've got UG here, I've got kinetic energy here. Then there's the snap. Let's ignore the snap for a second and go right over here to when it leaves the ground again and do another set of LOLs, right? And we've got the popper and we've got the earth still. Well, it may be a little nebulous what's happening right here. So let's go back to up here. What do we have at this point? And that's the after. That's our second one. Well, UG, KE, US, thermal. No air resistance. We are at a height again. So we've got potential energy. In fact, we have more of it than we did before, right? Because we went higher. Right? I don't know how much higher, but who cares, right? When it's at its maximum height, it's not moving. And now we can really say there's nothing going on with the spring, right? Because the spring has popped. But again, no change, so it's a little boring. We're going to forget about it. UG, KE, US. All right, now let's focus down here. If you think about this, well, it's at the bottom, no height. Again, even if there was a spring energy, it's deployed already, so we'll skip that. That means that we have all this kinetic energy as we leave the table. And that should make sense to you because if you didn't have the kinetic energy, how would you get to the height at the top? Okay? Now I am judiciously ignoring the snap in here, but I'll get to that in a minute. All right, since these are not all the same, I mean, let's face it, they're opposites of each other, but my amounts are not the same. Let's call this 1. Let's call this 1. Let's call this 2. Let's call this 2. And as we know, when we do LOLs, is we can make formulas out of those, and that's what's important. So UG1, or when we drop it up here, there's our 1s, right, equals kinetic energy 1, kinetic energy 2 equals UG2. And from here, you can actually figure out the first 3 questions, which was, you know, V at impact, V when leaving the ground, and although I didn't write it, well, I wrote this one, final UG. You know what's helpful to also know? Initial UG. So this is UG number 2 and that's UG number 1. Now why is that helpful? Let's make up some fun numbers here. I'm gonna spare you the actual calculation because I think you're smart enough to put in MGH over here, 1/2 MV squared over here, and do the math. Okay, but let's just pretend that we had, I don't know, 500 joules, which is ridiculously big, and then we only have 100 joules to start with, right? So when you dropped it from this height over here, there was 100 joules that changed to 100 joules of kinetic, and then magically it goes here and it has 500 joules, that becomes 500 joules up here. Well, what does that tell you? We added 400 joules, didn't we? And where did that come from? Well, hopefully it's obvious. It came from the popper. But when we add energy to something, that is what we call doing work. Okay, so that is where the idea of work is coming from. Work is a transfer mechanism. It is adding or reducing the amount of energy that you have in a system. So you have, just by subtracting these two, you can figure out the amount of work in the system. That is really, really helpful for 4, 5, and 6, because let's face it, number 4 says how much work is being done. And you just figured that one out by doing a simple subtraction. But you can't approach it from a force times distance perspective because you don't know the force. You know the distance. I did have a couple of folks say, well, wait a minute, I could figure out force if I know acceleration. I can do F equals ma. Wow, that's great thinking, and it really is, and you would be absolutely right, but it would be almost impossible to figure out graphically based on the situation that we have here. So it's kind of that rabbit hole that you're going to do a lot of crazy math and get yourself stuck. So this is a much simpler route to figure out the amount of work that's being done. Once you've figured out the amount of work being done, question number 5 is asking you for the force of the popper. Well, there you can apply what you know about work. Okay, work equals force times distance. Then this becomes, well, what's the distance? And there can be some confusion here because, you know, you have a distance down and you have a distance up, but ask yourself, when does that energy change? It changes when the popper goes from this to this. So what's the distance of the work? It's actually the height of the popper. So once you measure that and change it from centimeters to meters, we saw a lot of metric mistakes going on. All right, then you should be able to find the force. Number 6's question, what is the spring constant, the K of the popper? Now this is where kind of the fluidity of energy and work kind of come together. We have said that the popper does work, but you could also classify the same 400 joules as spring energy. See what I mean? It just depends on how you want to phrase it. And how do you know which way you want to phrase it? Because what makes the math easier for you, right? But it's the same 400 joules, but you could say, okay, that is my spring energy. My spring energy is 1/2 kx squared. What's the compression? Oh, it's that same distance, that same height of my popper. Okay, so you've got all of those things in there. I like this activity because it forces you to see where work is coming in something a little bit practical, I suppose, although I don't know how practical poppers are on a daily basis, but you get the idea. All right, so if you are still struggling with this lab or trying to see like the big picture of this lab, hopefully this helps you out just a little bit. It's a great way to say, where do I take those snapshots? Some of you tried to start by going from here to here. And then this part, well, what do I do about the snap? That became very difficult. So if you take other snapshots instead, let's call that one KE2, I never even labeled it, and UG2, then you can see that, maybe different snapshots make it a little bit easier, right? And then we can figure out what's going on here a little bit later. But taking those snapshots, making those into equations that then you can solve for missing pieces, that's critical in energy conservation. And then realizing that if the energy overall is changing, whether it's going up or down, we can call that work. And then we can do some figuring from there. That's kind of that's the big picture. That's what I was really hoping for you to see. I did see a lot of other things in the meantime, but overall that was the goal of our lab, and hopefully you find this helpful. Have a good one.